Still 4 lobes total in the molecular orbital. The 2 lobes that overlapped have shrunk in size, but did not entirely disappear. Although the molecular orbital formed from s orbitals is similar in shape, it only has 2 lobes.
Old Spice Super Hydration keeps me 24/7 moisturized and smells like a Fiji vacation.
This molecular orbital is a bond named sigma s plus pz orbital. We can tell it is a sigma bond because rotation around the bond is symmetric, and the bond involves an s orbital, which can only participate in sigma bonding. Because the lobes that are overlapping with one another are the same phase, the orbital is bonding, and the atomic orbitals come together to make one area of electron density between the nuclei. Because this molecular orbital is formed from the overlap of 2 different types of orbitals, both the s and the p orbitals are indicated in the subscript, separated by a plus sign. Overlap between s and p orbitals can occur if these orbitals are sufficiently similar in energy. Recall that an s orbital would not be able to overlap with a py or a px orbital, because it would be overlapping with a node. This is an example of a scenario where no bonding will occur. Because the py orbital is oriented vertically and the px orbital is oriented towards and away from the screen, the lobes are not able to overlap. Therefore, no molecular orbital can be formed from this orientation. Note that when combining p orbitals, overlap can only occur if they are in the same orientation. For example, a py with a py orbital, a px with a px orbital, or a pz with a pz orbital. The molecular orbitals for the H2 plus ion form from the 1s atomic orbitals of 2 hydrogen atoms. These 2 atomic orbitals come together to form 2 molecular orbitals, a sigma 1s bonding molecular orbital and a sigma 1s star antibonding molecular orbital. An H2 molecule with neutral charge would have 2 electrons, both in the sigma 1s bonding molecular orbital. Note that in order to achieve a positive charge, an electron will need to be removed. In this case, removing 1 electron will result in a charge of +1. This means there is a total of 1 electron to place in the molecular orbitals. This completes the molecular orbital diagram for the H2 plus ion. The molecular orbitals for the H2 plus ion form from the 1s atomic orbitals. This is an example of a scenario where no bonding will occur. This molecular orbital is a bond named sigma s plus pz orbital. This molecular orbital is an antibonding sigma pz orbital. We can tell it is a sigma bond because the 2 p orbitals are approaching one another head-on instead of side-on, and rotation around the bond is symmetric. Because the lobes that are overlapping with one another are
No, just wait. God.
This module will discuss how aqueous acid-base equilibria are described qualitatively. In chemistry, data can either be qualitative or quantitative.
Yeah.
Qualitative data is descriptive and refers to something observable. Observations like the color of a substance, the formation of gas bubbles during a reaction, or smell are examples of qualitative data that may be used in chemistry. By contrast, quantitative data is measurable and can be expressed in numbers. A qualitative description of an acid or base tells us about the strength of that acid or base, whereas a quantitative description will tell us about how much of each is present. In this module, we'll be discussing qualitative descriptions of acid and bases. There are a few different models that chemists use to describe an acid-base reaction. In this module, we will focus on the Bronsted-Lowry model, which defines acids and bases based on their abilities to either donate or accept protons. When acids and bases react with one another, the acid will donate a proton to the base, which accepts the proton into its molecular structure. Note that water can act as either an acid or base. When a water molecule reacts with an acid, it will act as a base and accept a proton. By contrast, when a water molecule reacts with a base, it can act as an acid and release a proton. Chemical species that can act as both an acid and a base are called amphoteric or amphiprotic. According to the Bronsted-Lowry model, an acid is a molecule or molecular ion that releases a proton. A strong acid can be generally represented by HX, where H is the removable proton. In aqueous solution, HX fully dissociates and the proton is accepted by water. Note that water is acting as a base in this case. We are left with X-, which is called the conjugate base of the acid HX. The hydronium ion H3O+, is formed when water gains an extra proton and is the conjugate acid of water. The 4 species make up 2 conjugate acid-base pairs, an acid and its conjugate base, and a base and its conjugate acid. Strong acids completely dissociate in water. We use the one-way arrow to indicate that the reaction goes to completion. This table shows the 6 strong acids that you must know for this course. Note that for sulfuric acid, only the first hydrogen is strongly acidic. We will talk more about acids with more than one dissociable proton later in this module.
Looking for a smarter way to mop? Try the Swiffer Power Mop. An all-in-one cleaning tool with a 360-degree swivel head that goes places a regular mop just can't. Swiffer Power Mop. Love it or your money back.
A Bronsted-Lowry base is a molecule or molecular ion that accepts a proton. Here we will discuss strong bases, which in water dissociate completely and produce hydroxide ions. This table shows the 6 families of strong bases. Here, M represents a group 1 metal, such as sodium, and M' represents a group 2 metal, such as calcium. You must know the contents of this table. Like spin metal, such as sodium, produce hydroxide ions. This table shows the 6 families of strong bases. Here, M represents a group 1 metal, such as sodium, and M' represents a group 2 metal, such as calcium. You must know the contents of this table.
This really ain't that hard. Like, I really do this shit though.
Like strong acids, strong bases completely release a stoichiometric amount of base, either through dissociation or reaction with water. The following reactions of strong bases show how they dissociate to produce hydroxide ions. Again, we use the one-way arrow to indicate that the reaction goes to completion. We place water, H2O, above the arrow when it acts as a solvent and is not actually reacting. We will now move on to discuss weak acids and bases. These are the acids and bases that do not fully dissociate in water. Consider the strong acid H2SO4. This acid fully dissociates in water, donating one of its protons to water. In this reaction, HSO4- is the conjugate base. However, HSO4- is also a weak acid due to the second acidic proton. In water, HSO4- also dissociates, but only partially. Because of this, it is called a weak acid. This equation shows the dissociation of HSO4-. We use a two-way equilibrium arrow called a weak acidic proton. This equation shows the dissociation of HSO4-. We use a two-way equilibrium arrow to indicate that the reaction is reversible. At equilibrium, the reaction occurs in both directions at the same rate, and the concentration of the products and the concentration of the reactants are constant, though not necessarily equal. This is the generic dissociation reaction for weak acids, where HA represents the weak acid. Another example of a weak acid is acetic acid, which you may know as the main component in vinegar. Here is the dissociation reaction of acetic acid and water forming its conjugate base, acetate. The curly arrow representation is something you will see often in organic chemistry. It lets us see how the proton transfer occurs. The arrows show how the lone pair electrons on the oxygen atom of water accept the proton from acetic acid, forming a new OH bond. This gives the hydronium ion H3O+. The reaction of a weak base into its conjugate acid can be shown by the generic dissociation reaction for weak bases, where B represents the weak base. Ammonia is a typical weak base. In water, it partially dissociates to form the ammonium ion.
Yeah.
What do you have for your problem?
I haven't even done it today.
Okay. I didn't mind us having two different prototypes and miscommunicating it.
What do you mean?
Like, you know how we thought we were doing two different things?
What?
You know, like a design, like half of us thought we were doing a full-ass greenhouse and half of us thought we were doing a bunker.
Okay.
I did that. But I kind of I over-exaggerated how bad it was.
Alright.
It's going up to YouTube though, so check it out.
Yeah. So.
Ion NH4+, which is its conjugate acid. Note that in this equation, water is acting as an acid. We can show the curly arrow representation for this reaction as well. Here, a new NH bond is formed when the lone pair on the nitrogen atom of ammonia accepts a proton from water.
Kashi layered fruit bars are proudly made in Canada with real fruit purees. They're oh so tasty. Grab a Kashi. Dry, brittle hair?
Give me more fucking
Need some
ads,
intensive
please.
care.
One more fucking ad, please.
Canteen.
This equation shows an equilibrium reaction in aqueous solution in which the reactants A and B give the products C and D. The stoichiometric amounts of each species are given by the stoichiometric coefficients, represented by the lowercase a, b, c, and d. The stoichiometric coefficients indicate how many molecules of A and B are reacted to produce how many molecules of C and D. The equilibrium constant K is defined as the ratio of products to reactants at equilibrium in terms of concentration, and is given by the following equation, where the concentrations of products are divided by the concentrations of the reactants. K has no units. The square brackets in this expression indicate concentration in moles per liter. In the expression, the equilibrium concentrations also have exponents, which are given by the stoichiometric coefficients. Let's look at the dissociation of acetic acid, for example. The equilibrium constant K can be determined by dividing the concentration of water. Therefore, we can represent the expression using this expression for the acid equilibrium constant Ka. Therefore, we can represent the expression using this expression for the acid equilibrium constant Ka. The following equations here show the generic equilibrium expressions for weak acids and weak bases. The subscripts A and B are used to denote a weak acid and a weak base, respectively. Therefore, Ka is the equilibrium constant for the dissociation of a weak acid in water, and Kb is the equilibrium constant for the dissociation of a weak base in water. We can use the equilibrium constants, Ka or Kb, to describe the strength of an acid or base. For instance, according to the equilibrium expression for a weak acid, a large Ka would mean that there is a high concentration of products and only a small concentration of the reactants, indicating a stronger weak acid. A small Ka would mean that there is a high concentration of the reactants and a smaller concentration of the product, indicating a weaker acid. The same trend is seen for weak bases and their Kb values. The Ka and Kb values for strong acids and bases can be viewed as approaching infinity, as these species completely dissociate in water with no reactants remaining. Since water is amphoteric, meaning it can act as either an acid or a base, water molecules can react with each other to form a hydronium ion and a hydroxide ion. The equilibrium constant for this reaction is called the auto-dissociation or auto-ionization constant, Kw. Kw is always equal to 1 times 10 to the negative 14. Ka and Kb values span a large range, so it's more convenient to use a logarithmic scale to describe the strength of acids or bases. The relationships between Ka or Kb values and their respective pKa or pKb values are given by the equations below. The lowercase p represents the negative logarithm. Note that this is an inverse relationship, meaning that a large Ka or Kb value will give a small pKa or pKb value. The Ka for a weak acid and the Kb for its conjugate base are related by Kw for the auto-dissociation of water. Shown here are the generic equations for the dissociations of a weak acid and its conjugate weak base. When added together, Ha and A minus cancel out, and we are left with the auto-dissociation equation for water, which you saw before. The K value for reactions 1 and 2 added together is equal to an expression that is equal to Ka times Kb. We can simplify this expression, again, canceling out Ha and A minus, to give the expression for Kw, which is simply the concentration of H3O plus times the concentration of OH minus. To summarize, for a conjugate acid-base pair, Ka times Kb is equal to the concentration of H3O plus times the concentration of OH minus, which is equal to Kw. Again, the product of Ka and Kb always gives the constant Kw, or 1 times 10 to the negative 14. We can take the negative logarithm of this whole expression to show it in terms of pKa, pKb, and pKw. We can use this equation to determine the Ka of an acid from the Kb of its conjugate base, and vice versa. We can also see from this equation that for a conjugate acid-base pair, the stronger the acid is, the weaker the base. Therefore, the conjugate base of a strong acid is an infinitely weak base. For instance, the conjugate base of the strong acid HCl is Cl-, which is infinitely weak and will not accept a proton from water. The case is similar for conjugate acids of strong bases, which are infinitely weak and will not transfer a proton to water. We are asked to identify which of the following compounds can be classified as strong bases. This can be determined using the general formulas for strong bases shown in the table below. Note that you must memorize the contents of this table. Based on this table, we can eliminate any molecules which do not have a group 1 or group 2 metal in the formula. Molecules which do not have an O or a hydridic hydrogen in their formula can also be eliminated. Finally, by comparison with the general formulas, we can see that the remaining molecules can be classified as strong bases.
Sometimes a man must overcompensate for his freshness. Old Spice.
Here we must complete the equation for the reaction of hydrogen sulfide with water. We know that hydrogen sulfide is a weak acid, so it will donate one of its protons to water. Adding another hydrogen to water gives the hydronium ion as our first product. When hydrogen sulfide loses this proton, it becomes the anion HS-. Water is a proton acceptor in this case, so it is acting as a base. The conjugate acid of water acting as a base is H3O+. This leaves us with HS-, which is the conjugate base of hydrogen sulfide. Here we are asked to write out the following reaction as a curly arrow representation. We can start by drawing the Lewis structures for both the reactants and the products. Next, we need to show how the proton transfer for this reaction occurs using curly arrows. Here, the lone pair on the oxygen of the acetate anion accepts a proton from water to form a new OH bond. So we draw an arrow coming from the lone pair and going to the hydrogen atom. We must also draw a second arrow coming from the original OH bond to the oxygen atom on water, which shows that that bond is broken. The first step for this question is to write out the reaction equation for the dissociation of formic acid in water. The equilibrium constant of a weak acid is found by dividing the concentrations of the products over the concentrations of the reactants. Remember that only aqueous species are included in the expression, so water can be removed from the denominator. This gives us the Ka expression for formic acid. Here we are asked to compare the strengths of two acids based on one Ka and one pKa value. To do this, we must convert the Ka of dimethylammonium to the pKa. We can do this by taking the negative logarithm of the Ka value. We can see now that the pKa of dimethylammonium is larger than the pKa of phenylammonium, so phenylammonium is the stronger acid. This question asks us to find a Kb value by starting with the pKa value of the conjugate acid. First, we can find the pKb for the conjugate base of dihydrogen citrate by subtracting the pKa value from 14. We can then calculate the Kb value, which is equal to 10 to the power of the negative pKb. And so our answer is shown here.
The last thing we need to do is ensure that these p orbitals are actually overlapping. At this point, we have now drawn all of the different bonds. And all that remains is to describe the last two bonds that we drew. In green, first we drew...
Polyprotic acids are acids which have multiple dissociable protons. Some examples are shown in this table. Note that Ka values decrease with each successive deprotonation, meaning that each proton lost is becoming less and less acidic. These are the structural drawings of the polyprotic acids from the table on the previous slide, with the dissociable protons highlighted in red. Notice that these protons are always attached to an electronegative atom, usually oxygen. This is because a negative charge is left behind on the atom in the structure when a proton is lost. This negative charge will need to be stabilized. And we know from Lewis structure rules that electronegative atoms are good at stabilizing these extra electrons due to their high effective nuclear charges. This is why the protons attached to the carbon atoms in citric acid are not considered to be acidic. If these protons were to leave, the negative charge would be on the carbon atoms, which is not electronegative enough to properly stabilize the remaining negative charge, especially when compared to oxygen. A common example of a polyprotic weak acid is phosphoric acid. It has 3 dissociable protons. The increasing pKa values for each reaction indicate that the acid strength decreases with each successive deprotonation. As such, H3PO4 is more acidic than H2PO4-, which is more acidic than HPO4-2-. We can also see from these equations that H2PO4- and HPO4-2- are amphoteric species, and they can act as either an acid or a base in water. To determine if an amphoteric species will act as an acid or a base, we must compare the pKa and pKb values. Let's look at HPO4-2-. In the third equation, HPO4-2- acts as an acid and has a pKa of 12.38, which describes its strength. In the second equation, HPO4-2- is the conjugate base of the acid H2PO4-, which has a pKa of 7.20. For a conjugate acid-base pair, the sum of the pKa and pKb is always equal to 14. Therefore, we can calculate the pKb of each PO4 2- by subtracting the pKa of its conjugate acid from 14. This gives the value of 6.80. Here is a summary of our results. The first equation shows HPO4 2- acting as an acid and is the same as the third equation from the previous slide. The second reaction shows HPO4 2- acting as a base to produce the conjugate acid H2PO4-. The pKb value of 6.80 describes the strength of HPO4 2- as a base. Since the pKb for HPO4 2- is smaller than the pKa value, we can confer that the basic properties of HPO4 2- will dominate in aqueous solution.
With Gillette Labs, my game face doesn't take days off. Gillette's ultimate shaving experience.
That's smooth.
In the first deprotonation, carbonic acid donates one of its protons to water. The product, HCO3-, has a negative charge due to the missing positive charge of the proton. The hydronium ion is also produced when water accepts a proton. Next, we write the second deprotonation reaction, which is the reaction of HCO3- with water. This produces CO3 2- and the hydronium ion. First, we write the equation for the isocitrate anion acting as an acid. When C6H7O7- acts as an acid, it donates one of its protons to water. This results in the product C6H6O7 2-. The hydronium ion is also produced when water accepts a proton. When acting as a base, C6H7O7- accepts a proton from water to form citric acid, which is C6H8O7. The hydroxide anion is produced when water donates a proton. A chemical species that can act as either an acid or base is called amphoteric. To answer this question, we must compare the pKa and pKb values of HSO3-. First, write out the equations for the first and second deprotonation of H2SO3, as well as the pKa values. We know that the pKa of the first reaction is 1.8, and the pKa of the second reaction is 7.2. Note that the second reaction shows HSO3- acting as an acid. Next, write the equation for the reaction of HSO3- acting as a base. We must find the pKb for this reaction. H2SO3 is the conjugate acid of HSO3-. To find the pKb of HSO3-, subtract the pKa of its conjugate acid from 14. We can now compare the pKa and pKb values of HSO3-. The pKa value is smaller, so the acidic properties of HSO3- will dominate.
In this short module, we'll discuss acidic and basic salts, specifically how to determine whether a salt will produce an acidic, basic, or neutral solution. We'll also learn how to calculate the pH of solutions containing acidic or basic salts. Salts can produce acidic, basic, or neutral solutions depending on the identity of the cation or anion present in the salt. There are three main rules we use to determine how a salt will affect the pH of a solution. If an ion is the conjugate acid of a strong base, or the conjugate base of a strong acid, the pH won't change, and the solution will be neutral. If an ion is the conjugate base of a weak acid, it will make the solution basic. If an ion is the conjugate acid of a weak base, it will make the solution acidic. Let's learn how to apply these rules by looking at a few examples. Is a solution of split range, and the solution will be neutral. If an ion is the conjugate base of a weak acid, it will make the solution basic. If an ion is the conjugate acid of a weak base, it will make the solution acidic. Let's learn how to apply these rules by looking at a few examples. Is a solution of sodium chloride acidic, basic, or neutral? Sodium chloride and produce sodium hydroxide and hydronium. However, we know sodium hydroxide is a strong base and completely dissociates in water. Therefore, the reaction between sodium plus and water doesn't occur in the forward direction, and sodium plus doesn't change the pH of a solution. Chloride reacts with water to produce hydrogen between chloride and water. Next, let's consider sodium acetate and water. Sodium plus is the conjugate acid of a strong base, sodium hydroxide, and doesn't affect the pH of the solution, as we have seen previously. Acetate is the conjugate base of a weak acid, acetic acid, and creates a basic solution. This makes sense if we look at the reaction between acetate and water. Acetate is a weak base and reacts with water to produce acetic acid and hydroxide in an equilibrium reaction. We have formed acetic acid, a weak acid, from acetate, its conjugate base. In doing so, we have also formed hydroxide, making the solution basic. Therefore, a solution of sodium acetate will be basic. Finally, let's consider ammonium chloride. Is a solution of ammonium chloride acidic, basic, or neutral? Ammonium chloride dissociates into ammonium cations and chloride anions in water. Chloride is the conjugate base of a strong acid, hydrochloric acid, and doesn't affect the pH of the solution, as we have seen previously. Ammonium is the conjugate acid of a weak base, ammonia, and creates an acidic solution. This makes sense if we look at the reaction between ammonium and water. Ammonium is a weak acid and reacts with water. In doing so, we have all...
Frosted Flakes good? They're great.
We've now learned that salts can produce acidic, basic, or neutral solutions depending on the identity of the cation or anion present. However, what if both the cation and anion can act as an acid and base? Calculating the pH. To predict the pH of a salt containing an acidic cation and a basic anion, we compare the Ka of the acid and Kb of the base. When the Ka of the acid is greater than the Kb of the base, the solution will be acidic. When the Ka of the acid is less than the Kb of the base, the solution will be basic. In terms of pKa and pKb, when the pKa of the acid is less than the pKb of the base, the solution will be acidic. When the pKa of the acid is greater than the pKb of the base, the solution will be basic. Let's apply these rules in some example will be acidic. When the pKa of the acid is greater than the pKb of the base, the solution. Begin by looking at the dissociation reaction of ammonium fluoride. Ammonium fluoride dissociates into ammonium cations and fluoride anions in water. Ammonium is the conjugate acid of a weak base, so it will make the solution acidic. Fluoride is the conjugate base of a weak acid and will make the solution basic. Since both ions affect the pH in different ways, we have to compare the pKa and pKb values of the acid and base to see which ion dominates in affecting the pH. We are given the pKa of ammonium, 9.25. However, we are given the pKa of hydrofluoric acid, not the pKb of fluoride. Therefore, we have to calculate the pKb of fluoride. Recall that the pKa of an acid plus the pKb of its conjugate base is equal to 14. Therefore, the pKb of fluoride is equal to 14 minus the pKa of hydrofluoric acid, or 14 minus 3.20. Therefore, the pKb of fluoride is 10.80. 9.25 is less than 10.80, so the pKa of ammonium is less than the pKb of fluoride. Since the pKa of the acid is less than the pKb of the base, the solution will be acidic. Let's try another example. Will a solution of sodium hydrogen sulfite be acidic, basic, or neutral? We begin by looking at the dissociation reaction of sodium hydrogen sulfite. Sodium hydrogen sulfite dissociates into sodium cations and hydrogen sulfite anions in water. Sodium plus is the conjugate acid of a strong base, so it won't affect the pH of the solution. Hydrogen sulfite is the conjugate base of a weak acid, sulfurous acid, and will make the solution basic. However, hydrogen sulfite is also a weak acid, forming sulfite. Hydrogen sulfite is therefore amphoteric and can act as an acid or a base. Since hydrogen sulfite can affect the pH in different ways, we have to compare its pKa and pKb values to see which one dominates in affecting the pH. We are given pKa values of sulfurous acid, so we have to write the two acid dissociation reactions of sulfurous acid in order to determine which values apply to hydrogen sulfite. Firstly, sulfurous acid will react with water to form hydrogen sulfite and hydronium ions with a pKa value of 1.77. Hydrogen sulfite is the conjugate base of sulfurous acid in this question, so we can determine its pKb from the pKa1 value of sulfurous acid. Specifically, the pKb of hydrogen sulfite will be 14 minus the pKa1 value of sulfurous acid, or 14 minus 1.77, giving 12.23. Therefore, the pKb of hydrogen sulfite is 12.23. The second acid dissociation of sulfurous acid involves hydrogen sulfite reacting with water to produce sulfite and hydronium ions with a pKa value of 7.19. Hydrogen sulfite is acting as an acid in this reaction, so the pKa of hydrogen sulfite is equal to pKa2 of sulfurous acid, 7.19. 7.19 is less than 12.23, so the pKa of hydrogen sulfite is less than the pKb of hydrogen sulfite. Since the pKa of hydrogen sulfite is less than its pKb, the solution will be acidic. Will a solution of sodium nitrate be acidic, basic, or neutral? We begin by looking at the dissociation reaction of sodium nitrate. Sodium nitrate dissociates into sodium cations and nitrate anions in water. Sodium plus is a group 1 cation and the conjugate acid of a strong base, so it won't affect the pH of the solution. Nitrate is the conjugate base of a strong acid, nitric acid, and will also not affect the pH of the solution. Therefore, a solution of sodium nitrate is neutral. Will a solution of triethylammonium acetate be acidic, basic, or neutral? We begin by looking at the dissociation reaction of triethylammonium acetate. Triethylammonium acetate dissociates into trimethylammonium cations and acetate anions in water. Triethylammonium is a weak acid, the conjugate acid of the weak base triethylamine, so it will make the solution acidic. Acetate is the conjugate base of a weak acid, acetic acid, so it will make the solution basic. Since both ions affect the pH in different ways, we have to compare the pKa and pKb values of the acid and base to see which ion dominates in affecting the pH acetate. Therefore, we have pKb of acetate is equal to 14 minus the pKa of acetic acid, or 14 minus 4.75. Therefore, is greater than
Old Spice Super Hydration keeps me 24/7 moisturized and smells like a Fiji vacation.
Ooh, can I try?
Will a solution of potassium dihydrogen phosphate be acidic, basic, or neutral? We begin by looking at the dissociation reaction of potassium dihydrogen phosphate. Potassium dihydrogen phosphate dissociates into potassium cations and dihydrogen phosphate anions in water. Potassium plus is the conjugate acid of a strong base, so it won't affect the pH of the solution. Dihydrogen phosphate is the conjugate base of a weak acid, phosphoric acid, and will make the solution basic. However, dihydrogen phosphate is also a weak acid, forming hydrogen phosphate. Dihydrogen phosphate is therefore amphoteric and can act as an acid or a base. Since dihydrogen phosphate can affect the pH in different ways, we have to compare its pKa and pKb values to see which one dominates in affecting the pH. We are given pKa values of phosphoric acid, so we have to write the acid dissociation reactions of phosphoric acid in order to determine which values apply to dihydrogen phosphate. Firstly, phosphoric acid will react with water to form dihydrogen phosphate and hydronium ions with a pKa value of 2.12. Dihydrogen phosphate is the conjugate base of phosphoric acid in this reaction, so we can determine its pKb from the pKa1 value of phosphoric acid. Specifically, the pKb of dihydrogen phosphate will be 14 minus the pKa1 value of phosphoric acid, or 14 minus 2.12, giving 11.88. Therefore, the pKb of dihydrogen phosphate is 11.88. The second acid dissociation of phosphoric acid involves dihydrogen phosphate reacting with water to produce hydrogen phosphate and hydronium ions with a pKa value of 7.20. Dihydrogen phosphate is acting as an acid in this reaction, so the pKa of dihydrogen phosphate is equal to pKa2 of phosphoric acid, 7.20. 7.20 is less than 11.88. So the pKa of dihydrogen phosphate is less than the pKb of dihydrogen phosphate. Since the pKa of dihydrogen phosphate is less than its pKb, the solution will be acidic. In this question, we're asked to rank 1.0 molar solutions of hydrobromic acid, magnesium oxide, ammonium chloride, potassium nitrate, and calcium carbonate in order of increasing pH. To answer this question, we'll have to analyze how each of these species interacts with water and affects the pH of the solution. Hydrobromic acid completely dissociates in water, making it a strong acid. Magnesium oxide reacts with water to form magnesium cations and hydroxide anions, making it a strong base. Ammonium chloride dissociates into ammonium cations and chloride anions in water. Ammonium is the conjugate acid of a weak base, ammonia, and will make the solution acidic. Chloride is the conjugate base of a strong acid, so it will not affect the pH of the solution. Therefore, we can consider ammonium chloride to be weakly acidic due to the ammonium cation. Potassium nitrate dissociates into potassium cations and nitrate anions in water. Potassium is the conjugate acid of a strong base, so it won't affect the pH of the solution. Nitrate is the conjugate base of a strong acid, so it also won't affect the pH. Therefore, a solution of potassium nitrate is neutral. Finally, calcium carbonate dissociates into calcium cations and carbonate anions in water. Calcium is the conjugate acid of a strong base, so it won't affect the pH of the solution. Carbonate is the conjugate base of a weak acid, hydrogen carbonate, and will make the solution basic. Therefore, we consider calcium carbonate to be weakly basic due to the carbonate anion. Increasing pH means most acidic to most basic. Based on our analysis, hydrobromic acid is the most acidic, followed by ammonium chloride. Potassium nitrate is neutral. Then, calcium carbonate is weakly basic, followed by magnesium oxide, which is a strong base. Therefore, the solutions ranked in order of increasing pH are A, C, D, E, B.
Hey guys, welcome back to
The acidity or basicity of a solution is of great interest to many everyday chemists. Acid-base chemistry can be performed in both a qualitative and quantitative manner, and with respect to this unit, we will be talking about quantitative acid-base chemistry. The acidity and or basicity of a solution can be described by pH or POH. pH measures the amount of hydrogen cations, also referred to as hydronium ions, H3O+, in solution, which increases when an acidic compound is added to water. pOH measures the amount of hydroxide ions in solution, which increases when a basic compound is added to water. The hydrogen or hydronium concentrations work in tandem with hydroxide ions. If the concentration of hydrogen or hydronium ions increases in solution as an acid is added, the concentration of hydroxide ions decreases, and vice versa. This occurs to maintain the equilibrium constant Kw. Here we have a useful expression where the equilibrium constant Kw can be expressed as follows, where Kw is equal to the concentration of the hydrogen ions multiplied by the concentration of the hydroxide ions, which equals 1.00 times 10 to the negative 14. We can report Kw and the concentrations of the hydrogen and hydroxide ions using a logarithmic scale called P formalism, where pKw is equal to the negative log of Kw, pH is equal to the negative log of the concentration of hydrogen ions, and pOH is equal to the negative log of hydroxide ions. By combining all of these relationships, we have pKw equal to pH plus pOH equals 14. This expression is useful because once you find either pH or pOH, you can easily find the other using this equation. Now we will discuss what the pH scale is. We can see here that something like hydrochloric acid is obviously acidic. This means the concentration of hydrogen ions is far greater than the concentration of hydroxide ions. Therefore, the pH is much closer to 0, indicating this is a strong acid. In contrast, sodium hydroxide is strongly basic because it has far more hydroxide ions present in solution than hydrogen ions. Therefore, the pH of sodium hydroxide is very close to 14. When the pH is 7, the solution is neutral, meaning there is an equal concentration of hydrogen and hydroxide ions.
Give yourself the gift of technology this holiday and easily share with friends and family. Give yourself more with the Kia Seltos and get a $500 holiday bonus this season.
Kia, movement that inspires.
Now let's talk about acid-base reactions. The reaction between an acid and a base is called a neutralization reaction. If a strong acid reacts with a strong base, the product solution will have a pH of 7 and be considered neutral. Here, we can see a reaction between a strong base, sodium hydroxide, and a strong acid, hydrochloric acid. This produces a salt, sodium chloride, and water, which we know has a neutral pH. Note that only one reactant needs to be strong for an acid-base reaction to go to 100% completion. A strong acid will react completely with a weak base, and a strong base will react completely with a weak acid. Furthermore, if an acid or base is not completely consumed in a reaction, the resulting pH will not be neutral, and we must find the concentration of the excess acid or base to determine the pH of the solution. To demonstrate that a neutralization occurs, we can look at two types of ionic reactions. First, we have the total ionic reaction. In this reaction, there are certain ions present on both sides of the reaction, called spectator ions. Spectator ions produce the salt in the neutralization process. Once we cross out the spectator ions on both sides of the equation, we obtain the net ionic reaction. In the net ionic reaction, we can see a neutralization reaction produces water, which is a neutral product. Now we will discuss titrations of strong acids and bases. A titration is an analytical technique that allows us to find the unknown concentration of a solution using another solution of known concentration that reacts with the first solution. In an acid-base titration, base is slowly added to an aliquot, a sample with a specific volume, of acid using a burette. The aliquot contains an indicator, which is a molecule that changes color based on the pH of the solution. The equivalence point of the titration occurs when the base has completely reacted with the acid. The end point of the titration occurs when the indicator changes color. Ideally, we want the equivalence point and the endpoint to occur at the same time. Then, using stoichiometry, we can find the unknown concentration of acid based on the volume of base used and its concentration. There are many different indicators we can use when performing a titration. We can see that different indicators will change color in different specific pH ranges. The pH indicator you choose will depend on the pH at which you expect your equivalence point to be achieved. Let's discuss the setup for an acid-base titration. We begin by pipetting a known amount of the acid solution into an Erlenmeyer flask. Next, you add indicator to your flask and place it under the burette.
I don't care about
Burette
this.
is filled with a base of known concentration, and the initial volume of the base is recorded. You then add base to the acid solution of unknown concentration. What is the pH of an aqueous solution of 1.3? What is the pH of an aqueous solution of 1.35 mole?
Might need that.
Another way to look at acid-base titrations is to plot a titration curve, which shows the change in pH of a solution as a function of how much base is added. Here we have a titration curve of hydrochloric acid, a strong acid, and sodium hydroxide, a strong base. The inflection point on the curve is the equivalence point, where the moles of sodium hydroxide have completely reacted with the moles of hydrochloric acid. Ideally, this is also the end point, where the indicator changes color, signaling the end of the reaction. The equivalence point will vary depending on the strength of the acid and the base. In this example, the equivalence point occurs at pH 7. In the region below pH 7, there is more hydrochloric acid present in solution than sodium hydroxide, and the sodium hydroxide is the limiting reagent. In the region above pH 7, there is only sodium hydroxide present in solution because all of the hydrochloric acid has reacted. What is the pH of an aqueous solution of 1.35 molar cesium hydroxide? First, let's write an equation for this reaction. Aqueous cesium hydroxide dissociates fully to form cesium plus and OH minus, as cesium hydroxide is an ionic compound. We know the concentration of cesium hydroxide is 1.35 moles per liter, and we can use this to convert to the concentration of hydroxide ions. We were not given a volume, so the volume remains constant in this problem. Therefore, we can convert from one concentration to another by using stoichiometry. In doing so, we find the concentration of hydroxide ions to be 1.35 moles per liter, or 1.35 molar. With this information, we use the following equation, where we fill in the concentration of hydroxide ions to get pOH equal to the negative log of 1.35 to obtain a pOH of negative 0.130. Note that a negative pOH means the concentration of OH minus is greater than 1 molar. Since the question asks for the pH of the solution, we must then convert pOH to pH with the following equation, where pH plus pOH is equal to 14. After filling the value of pOH into this equation, we see that the pH is equal to 14.13. Again, since cesium hydroxide is a strong base and has a concentration greater than 1 molar, we get a pH greater than 14.
Dry, brittle hair? Needs some intensive care. New Pantene Damage Repair
Show the
Collection.
video your
Our
new
formula with
blanket.
provitamins, argan, and jojoba
Show the
oils
video your new
regenerates hair
blanket.
bonds at the molecular
Well.
level for healthier hair at a fraction of the cost. Pantene.
What you mean video?
If 2.90 grams of sodium oxide with a molar mass of 61.979 grams per mole is dissolved in 150.0 milliliters of water, what is the pH of the resulting solution? Assume the volume is not affected by the addition of the solid. First, let's write out the chemical equation for the reaction of sodium oxide with water. Next, we must find the moles of sodium oxide in order to find the moles of OH-. We divide
Knock on his
2.90
door,
grams of sodium
show him
oxide
your
by its
blanket.
molar mass to find 0.0468 moles of sodium oxide. Through using the mole ratio between sodium oxide and OH- of 1 to 2, we convert the moles of sodium oxide to 0.0936 moles of OH-. To find the concentration of hydroxide ions, we divide the moles of hydroxide ions by the volume of water that sodium oxide was dissolved in liters, giving 0.624 mole. We then find the pOH through the use of the following equation, filling in for the concentration to find that pOH is equal to 0.205. We then convert pOH to pH to find that pH is equal to 13.80. This is a strongly basic solution, hence the very low pOH value and very high pH value.
The water running in the fucking kitchenette.
Determine the pH to 2 decimal places of the solution that is produced by mixing 40.0 milliliters of 3.30 times 10 to the negative 2 molar perchloric acid with 40.0 milliliters of 1.09 times 10 to the negative 2 molar hydrobromic acid. Note that both of these acids are strong acids, so they will fully dissociate to form hydrogen ions. Let's start off with perchloric acid. Here is the dissociation reaction for this acid. We must determine the number of moles of hydrogen ions, so we use the moles of perchloric acid to convert to hydrogen ions, and then multiply by the volume of perchloric acid in liters to find 1.32 times 10 to the negative 3 moles of H+ in the perchloric acid solution. Now let's find the moles of hydrogen ions in the hydrobromic acid solution, described by the following equation. Following the same process as above, we find there are 4.36 times 10 to the negative 4 moles of H+ ions in the hydrobromic acid solution. Next, we find the total moles of hydrogen ions in the solution by adding the amount of H+ ions from perchloric acid and hydrobromic acid. This gives us 1.76 times 10 to the negative 3 moles of H+ ions. We then divide the total number of moles of hydrogen ions by the total volume of the solution in liters to find 2.20 times 10 to the negative 2 moles.
Alright, hold on.
I understand my thing is tough, Campbell.
Yep.
Where is that as a cape, Campbell?
I'm not where. You go ahead. You got it, buddy. Yep.
Is that tough or what?
Very
Molar
tough.
of hydrogen ions. Lastly, we solve for pH by plugging this concentration into the following equation, where we obtain a pH of 1.66.
What topic are you on?
Determine the pH to 2 decimal places of the solution that is produced by mixing 65.3 milliliters of 7.59 times 10 to the negative 3 molar hydroiodic acid with 4.18 milliliters of 2.48 times 10 to the negative 3 molar magnesium hydroxide. We first need to determine the limiting reagent and the excess reagent. We'll start with the dissociation of hydroiodic acid, a strong acid that completely dissociates in water.
Yes, you don't.
Looking for the moles of H+, which can be determined by converting.
Alright.
Yeah.
I should probably do some practice questions. I understand.
They take the questions from the exam bank of the topic 9 till 12, right? Or oh, okay.
You want to do them with me? We can do a
Probably
couple.
tomorrow. I haven't even finished all of the videos yet. I need to finish watching all of the videos.
Alright, then I'll do my video for whatever, and then
Study with Campbell.
what?
Study with Campbell.
No, Campbell Studies? That's the YouTube channel, bro.
Campbell Study.
Nobody back home would believe it. But
I just subscribe, Campbell.
nice, thanks.
Oh shit! I see myself.
How to get fucking yoked? Shoot up 400 milligrams of gear a day.
What? 400 milligrams of gear?
Yeah. You can take any stack you want. Tren, just regular test. You could probably go like anything anabolic, really. You want to minimize the androgenic, like steroids that make you lose your hair and stuff. But basically anything that's that won't like decompose into like what's it called? Is it? It's not TOT. It's
Deca? You tried Deca?
No, Deca's fine. Androgenic.
Henry told me if I don't get 8 reps on like my chest fly,
yeah,
I would have to go on steroids. Like I have to blast steroids. No, I get to blast steroids. I got 8 reps, by the way.
Nice. Yeah, so androgenic steroids, they kind of they'll make your voice deeper. They'll make you like They'll make your hair fall out. They'll probably make you fatter, like less lean. But so you really want to stick to more like a higher anabolic to androgenic effect. So things that kind of max those out. That you can find a table online pretty easily. So shit's a banger, isn't it? Here, so testosterone has like a 1-to-1 anabolic androgenic ratio, and then you can find better ones like here, stanozol has like a 30-to-1 anabolic androgenic, but you obviously run into pretty bad side effects usually. So stanozol, brand name Winstrol, synthetic anabolic androgenic steroid, performance enhancing drug. So stanozolol versus test. It's just effective overall, I'd say. Like, more effective. So, really, don't waste your time just pinning up Trenton and test. I think Tren's actually pretty effective. Let me look up. Tren anabolic to androgenic ratio. Actually, it's pretty 1-to-1, but though some research suggests it might bind to androgen receptors even more strongly than DHT, making its effective ratio exceptionally favorable for muscle despite its powerful side effects. Yeah, so basically you get really screwed up with Tren, but it works really well. Yeah. Activating androgen receptors. Does Tren make you bald?
Depends.
Yes, it does accelerate male pattern baldness. So yeah, obviously your hair has androgen receptors, so if Tren binds to those as well as the ones in your muscles, it will make you lose your hair. Hopefully you have androgen receptors on your face that help you grow a beard to compensate, but if it doesn't, that's pretty unfortunate. You'll go bald and you won't get a beard, but you will be pretty jacked. So ideally you find another steroid that has a better anabolic to androgenic ratio, but you can always just pin up Tren. It'll work pretty well. David, what do you think?
What?
You got anything to say before I end this video and post it? Pretty short, 40 minutes, but I already put up a 2.5-hour one today, so this is probably the most commentary I've done so far. What do you think?
I think everyone watching this should like.
Defect GI. Your country lies to you, GI.
What's GI?
GI? It's like the soldiers.
Oh, like
the American soldiers. They were called GI.
Oh, okay. Thought you were saying like the company and like people controlled by Palantir.
No. Palantir, they control everything, dude.
Yeah.
It's whatever. They're gonna own people, dude.
Are they gonna take
your data? The data that you create is more valuable than you. That's what they say now.
Oh my God.
So it's pretty bad. But anyway, nope. Stop. Alright. Hit that like and subscribe button. Make sure you turn the bell notifications on.